All right. Thanks everybody for coming to our seminar today. This is again an SDSU TILOS research seminar. We're hosting in collaboration with our colleagues at the Institute for Learning and Optimization at Scale as part of our Expand AI NSF project here at SDSU. So it's my pleasure to introduce Jeremy Schwartz, who is a senior manager on the planner team at Zoox. I'm going to let him tell you more about a little bit about his background and his journey.
Yeah, thanks. All right, welcome to my talk. I call this 95% bridging the gap between prototype and product. Why do I use this name? It's based on an expression that I love to hate, which you may have heard, which is that the last 5% of the work takes 95% of the time. It's a stupid expression, but I do think there's a grain of truth underlying it. I think what it's really trying to get at here is that a prototype can seem like it's 95% of the way to a solution, but in reality, it's only 5% of the way to a real product. So that's what I'm sort of trying to illustrate here. This talk is going to discuss the reasons for that gap and how to bridge that gap during product development. First of all, I want to give you a little bit about my background. I graduated from MIT with a bachelor's and a master's in mechanical engineering with a focus on robotics. Since then, I've had a 20-year career in a variety of industries, developing software for aerospace and ground vehicles. I started my career, my professional career at Northrop Grumman Space Technology, which is a satellite arm of the large defense contractor. My work there was in formation flight for satellites. In other words, controlling groups of satellites flying cooperatively in close proximity. I then had 2 years at my own engineering firm called Mitrio, mostly continuing work on satellite research. And then I spent 2 years at a company called Applied Minds. This company was basically an invention lab. Other companies, like Northrop Grumman, would actually hire Applied Minds to build creative prototypes for them. All three of these roles were really R&D oriented. There were lots of exciting projects. It was really cool, like formation flight in space. It's cool stuff. But at the end of each project, we would do a demonstration for our bosses or our customers, and they would, applaud and pat us on the back for being so innovative, and then the project would just get mothballed. And so it really was, it became very frustrating for me to watch all of this exciting, research not really turn into anything practical. So I really wanted to make a change to focus on companies that were really kind of like laser focused on developing commercial products. So I then went to a company called Zipline for 5 years. I was actually a very early engineer at Zipline. I think I was employee number 13, if I remember correctly. Zipline, if you're not familiar, is a company that does delivery of critical medical products by drone. And actually, they're expanding out now, I should say, to commercial products as well. But where we really started was in being able to deliver things like blood and medicines by drone. I helped actually build the entire flight software stack there. And I think my proudest thing was an autonomous deconfliction strategy, basically fully autonomous distributed air traffic control for the fleet of fixed wing delivery drones. Since then, actually right when the pandemic started, I left Zipline and I joined Zoox. This company is building a robotaxi similar to Waymo. The big differentiator between Waymo and Zoox is that Zoox is actually building a car from the ground up. The car actually looks more like it's been likened to a 1950s toaster. Or I actually think what it really looks like is a gondola on wheels. It's got these French doors. There's no steering wheel. You just walk in and the seats actually face each other. Because one of the neat things about the car is that it's bi-directional. I can just pull into a spot going one way and pull out of the spot going the other way. It's a neat trick. So both of these companies have been laser focused on bringing a product to a market that needed it. So basically, my background has been split in half. The first half was focused on making effective prototypes, and then the second half has been focused on bridging that gap from prototype to product. Okay, so I just want to go over a quick agenda. Basically, first I'm going to talk about, hey, what's actually the difference between a prototype and a product? Then I'm going to go through a case study, which is the recovery system that we built to recover the Zipline fixed wing drones. I think it's a fascinating example, and you can really see the evolution that occurs over time during product development. Then I have a slide on important questions that come up in product design that you should be asking yourself. And then finally, most of my talk is going to be sort of software oriented because most of my career has been in software development. And so I'm really going to talk about two important concepts that I consider to be critical for designing mature software. Okay, so what is, I've been talking about a prototype, very different from a product. So what's actually the difference? Prototypes are designed to open our eyes to possibilities. They're generally designed to be effective demos, right? Prototype code, when we're talking about software code, it's really built for the happy path. And what I mean by that is you want to show what's possible when everything is working as intended. If something goes wrong, you're generally better off stopping as quickly as possible, finding and fixing the issue, and then restarting, which is why you see a lot of asserts in prototype code, because as soon as something's suboptimal, you probably want to just figure out why and fix whatever caused that to happen. A success rate of a prototype, if it's 4 out of 5, it's pretty good. You're showing somebody a demonstration, you have to restart once. Nobody's really going to bat an eyelash at that. Prototypes are not built for durability or longevity, right? They generally expect experienced users who can turn the right knobs and pull the right levers to get the thing to work correctly. They're also used in a controlled environment under optimal conditions to show off, again, sort of the desired capabilities or the possibilities. Products are different because they need to work all the time. Just think about like your cell phone and just imagine if your cell phone, crashed every day or even once a month, and how frustrating that would be. Products do not operate on the happy path. They need to handle all manner of things going wrong. Practically speaking, when we're actually talking about, again, a software program, they can't halt execution. So where, like I mentioned, asserts are really good in prototypes because you want to just stop immediately when something is off nominal. They're your enemy in a product. Again, thinking about your cell phone, imagine if your cell phone was just like, oh, assert, failure, blue screen of death. It would be entirely unacceptable to a customer. Some of the challenges that you have to deal with a product include things like confused users or even antagonistic agents involved in the situation. And the environment is completely uncontrolled. I mean, it's in some cases to the point of chaos. One of the things that I've learned, especially at Zoox, is that they often use the term structured versus unstructured environments. Well, unstructured environment is a euphemism for what happens out on the road, right? I mean, there are hypothetically rules of the road, and we should be following those rules, but lots of other agents in the scene do not follow the rules of the road. And in fact, in some situations, you can't follow the rules on the road if you want to use it like a human being or use it, sort of reasonably. Like imagine having to pass a car that's double parked on a street that's just one lane each way and having to cross that yellow line, which technically you're never supposed to cross. So one important note of caution I'll add here, it's really important not to mistake a prototype for a product. A lot of startups, including, this is a picture of Theranos for those who are familiar, they oversold their prototypes and then they failed when they were unable to convert that prototype into a mature product. All right. So now I want to talk about the zipline recovery system. This is super cool sort of history going back to the early days of zipline back in probably about 2017 or so, 2016, 2017. So this system right here is actually the first version of the zipline recovery system. It's hard to see, so I apologize for that, but these are actually fishing poles, like literally deep sea fishing poles. There's a string strung between these two fishing poles, and then there's this giant, literally it's a moon bounce. We got it made by a moon bounce company, like you have for kids' parties. So it's a constantly inflated mat. And the idea is that the plane flies over the line. I should point out, this is actually a very important detail as well. So here's the plane right here, flying on the second version of the system. And really thin line right there is actually the deployed tailhook of this plane. So it actually had this meter-long hole with a hook on the end, and it would be stowed just back during flight, and then it would deploy that hook when it wanted to land, and it would just fly over that line over and over until it caught the line. It was great. I mean, it got the plane out of the air and safely on the ground without needing a landing strip. So it really demonstrated the ability to have like a drone port, an airport for these drones with a pretty small footprint, right? We didn't need a runway in order to land these planes. But it had lots of problems when it came to actually making a product out of this. For one, it took a lot of passes to get that plane on the ground because when a fixed wing plane gets that close to the ground, it has a lot of turbulence due to ground effect. And so the plane would have a lot of vertical disturbance and it would kind of be going like this. And sometimes it would catch the line and sometimes it wouldn't. And having to go around every time, it's fine for a demonstration. But if you're doing 150 or 300 flights a day at this drone port, having to go around and do multiple passes, and taking 5 minutes each time is just unacceptable. Similarly, running out on that moon bounce was actually really fun, like the first 2 or 3 times. You're an adult on a moon bounce, and it's a ton of fun. And then after that, it gets really tiring. Imagining that our flight operators would actually run out there and grab those planes. Again, when they're doing this 200 times a day, it's just unrealistic. Another problem, if it rains, rain would fall on the mat, and then as soon as the plane landed on the mat, it would create a little depression, and all the rain would collect in the depression and would flood the plane. So, this thing has to operate in the rain. Another issue with this, if a plane hit that line, like if the disturbances from the ground effect caused the plane itself to drop in the line and not the tail hook, that was a catastrophic failure. The plane would go flying, it would tumble, it would crash into a million pieces. We'd lose the plane. So we have a second version here, and it solves a lot of these problems, right? So for one, you might notice the mats are much shorter and they're actually sloped. So that immediately solves the rain problem. Sloped mats, right? Rain doesn't collect on the mat. Because they're shorter, the reason they were shorter is because we could control the stopping distance more precisely. And the reason we could do that is because instead of just fishing lines with a reel, we had active motors. And so they could control when the vehicle would stop and could therefore stop it on a much tighter, much smaller pad. And because of that, it meant that the operator didn't even have to go out on the pad. They could literally stop the plane on the edge of the pad. The operator would go, walk up, grab the plane off, and prepare for the next flight. Also, those poles are on, in addition to having motors for controlling the line, there were actually motors for rotating the poles. That way, if the plane was coming in too low, the poles could actually drop out of the way, and it will eliminate that catastrophic, mode of failure. So it solved those problems, and I actually have a little video, and I'll play this video, and I'll just have the sound on for the first one, because there's an interesting thing about this. Do you notice when it lands, you hear it throttling up? That's actually a design element. The reason is if the plane doesn't recover, if the plane is not captured, you need to gain speed in order to gain altitude in order to not crash. But setting that aside, what you see here is you see the plane just, those poles had that line up in the air. The meter-long tailhook catches on the line. The plane is caught, and then the motors control so that the plane lands right nicely at the edge of the moon bounce. So it solved a lot of those problems. However, this system also had a lot of problems. Those mats that I mentioned, they were big, they were loud because they needed to be constantly inflated, and they were expensive to make, and also because they needed to be constantly inflated. Another issue that we had, that tailhook mechanism that I mentioned, that would fail to deploy sometimes. And that would be a real problem because, well, now you've got this plane, it doesn't have any landing gear, the tailhook is not deployed. How are you going to recover the plane? Usually we just had to ditch it when that happened. And an interesting one about this actually is that you don't necessarily realize, you don't necessarily think about, well, I guess all of these things are things you don't necessarily think about until you try them. But it still needs a lot of room around the drone port in order to do this recovery. Even though the drone port itself is pretty small footprint, the plane has to come in at a reasonable glide path. And so it still needed like a soccer field worth of space in front of this system in order for the plane to come in and be recovered. And that meant that we couldn't place it near like one-story buildings. So then we get the third iteration of the system. It's really incredible. I do have a video of this as well. And it does active line capture. This system has much stronger motors that are controlling these poles. And the motors are actually so strong that they are able to hold the line out of the way as the plane passes over the system and literally whip the line up into the plane between the wings and the back of the boom. And because that active system could do that, it actually solves a lot of those problems I was describing before. One, it's completely eliminated any chance of a catastrophic failure because the line is completely out of the way when the plane actually flies by. Second, it completely eliminated the need for a deployed tailhook. The tailhook actually turned into this tiny little fixed hook on the back of the boom because that line would whip up into the boom and then it would ride back along the boom and catch that tiny little hook. And so it eliminated moving parts for this system on the vehicle. Nothing to fail on the vehicle, right? The vehicle hangs down right in the middle there for easy recovery. The operator just has to walk out into the pad and grab the vehicle off the line. And the additional height of this thing actually is another advantage because it means now that glide path can come in above one-story buildings, right? Another neat thing about this is that you can actually see in the pictures here, right here is actually a joint. So this entire system could be made to kneel so that operators that had to do any kind of service on the poles or the motors didn't have to go get on a ladder to do it. They could just bring the system down and do the service they needed to do. And by the way, I should say it wasn't a straight path from A to C, right? There were many alternatives considered. I was involved in one alternative where we tried to use spring-loaded poles to do that spring action that I was talking about. And actually, let me tell you, it was quite terrifying. We used pole vault poles, and taking pole vault poles and mounting them up, or sort of loading them up so that they're in the loaded mode. Imagine being next to a 10-foot-long mousetrap. You really didn't want to be anywhere in the vicinity when that thing fired. So yeah, it takes a lot of iteration to get there. I do have a video of this one as well. I think it's just a GIF. But there's a lot of things that are worth looking at here. One, you can actually see, if you look right there, you can see the whip motion where those poles just snap up and catch that plane as it crosses over the line. Another thing that I think is really interesting is if you look, the plane comes all the way to there in order to be recovered.
Okay.
The landing system is actually doing a lot more even at that point, because at that point, if it just let it swing down, I mean, it would just slam into the ground, right? So it's actually actively reeling it in as it comes down in order to control, have a controlled recovery.
Yeah, no, I hear what you're saying, yeah.
Is that me?
No, I don't.
Okay. By a 3D television, and in fact, it created a lot of annoyance because you need to have special glasses, you had to be sitting in certain places, so it actually created some friction to the way people like watching TV. So yeah, that's really the question here: do they want to buy it, or do I just want to make it? The second question you should ask yourself: do you actually understand the problem? So this is, I think, commonly called ivory tower syndrome, where you see a problem and you're like, okay, there's a problem here. There's definitely an issue. We can go fix this issue. And then you go away into your own little area, your own little ivory tower, and you go design a solution to that problem. And you're like, yes, I've got the perfect solution. I'm going to go release it upon the masses, and it's going to solve all their problems. And then you come out and you present your solution. And they're like, well, that actually isn't the problem that I'm dealing with. I think AR goggles are. Actually, these are a good example of this third one, but a good example of the ivory tower one is, we're trying to. I worked with groups that tried to solve problems of energy in developing countries where they like didn't have enough fuel to like burn for fire, for food. And they came up with all these ways to do like charcoal briquettes, but they use these complex machines. They use these like machines that required a lot of maintenance and a lot of precision parts in order to make them. And the problem is they would bring them to these countries that didn't have any ability to manufacture replacement parts. So those devices would work until they stopped working, and then they were useless. And so all those systems ended up being impractical for that reason. The third one here: does your solution really solve the problem? So let's say you've identified a problem and you think you really understand the problem. Generally, if you do those first two well, then the third one should be pretty easy. You should be able to answer this question pretty easily. But one trap that can happen here is, your solution might not actually be good enough. So, the example that I give here is, if you guys remember the HoloLens, was, augmented reality goggles. This was something that, this was sort of the promise of it was like, oh my God, we're just going to be able to operate. We're all going to wear these things and we're going to be able to manipulate holograms in our space. And it's going to be like Minority Report and it'll be amazing. The problem is that the actual practical technology was so limited that like the field of view was, literally just the area directly in front of you. It wasn't bright enough, and there were all these things that just made it not actually a practical solution to the problem. So really, yeah, ask yourself these three questions when you're thinking about developing a product. Okay, so the rest of my talk is going to be focused on specific software design practices that I really like to recommend in order to make your code that you're developing mature enough to support a product. So how do we design for mature products? There's many ways to answer that question. There's really two attributes that I want to focus on: maintainability and robustness. Each of these two categories have several dimensions in their own right, and I'll spend the rest of the talk covering a few of those dimensions. So first, let's talk about maintainability. The first principle I want to address is legibility or readability. Right? A good way to test readability is to ask yourself, how long would it take a new employee to understand this code when looking at it for the first time? And you might think that's a silly question. If you're the person responsible for maintaining your code and you understand your code, you might think that's good enough. But here's a secret. You're going to forget. When you work on a product, you may do a dozen different projects in 6 months. And then if you have to come back in 6 months or in a year, you're not going to remember. You're going to come back to this code and you're not going to have any recollection of writing it, and you're not going to remember the clever thing that you were thinking of doing when you first wrote it. So you're not going to remember the rationale that you thought was obvious at the time if you can't read the explanation in the code. So one of the expressions I love, I don't remember where I got it from, but comments are love letters to yourself in 6 months. And another tip that a friend always likes to point out that I think is a good one: if you think you're being clever when you write the code, that's a warning sign. It probably means it will confuse you when you come back to it. So what is the difference between a good comment and a bad comment? Good comments explain why the code does what it does. That's it in a nutshell. It's explaining why. So things like explaining the reasoning behind, or the logic behind some constraints in the system, or the reasoning behind some logic in the system. Comments that are clarifying complex algorithms or optimizations. Comments that document non-obvious edge cases or workarounds that are being implemented, providing context for design choices. Some of my favorite comments actually explain, oh, we're using such and such algorithm from this paper, which can be found here, and actually just literally embeds a citation hyperlink right into the comment. It looks kind of funny in source code, but it's actually proven very useful on many occasions. So what are bad comments by comparison? And I think hopefully you can see the check mark here. This is my very simple example of a good comment and a bad comment. And this is oh my God, even worse. So what are bad comments? Redundant or obvious comments. You don't need to write what the code is doing. People can read. They can read the code. They can figure out that this is what's happening here. And then, even worse is outdated comments, where I mean, this isn't necessarily outdated. This is just plain wrong. This is sort of, but what can get really bad is where you write a comment, it makes sense at the time, and then somebody changes the code, they don't change the comment, and now you've got this confusion where it's like, well, is the code broken or is the comment wrong, or how do I figure out this discrepancy? Of course, also just comments that are flat wrong are obviously confusing to people. Make sure to avoid those. I think that one's probably obvious. Okay, so then the other property I would say of readability or general of legibility is modularity. Used properly, modularity helps limit the complexity of a system by subdividing it into simpler subproblems. The components are simpler than the whole, right? Interfaces give clear definitions for required inputs and resulting outputs. But a word of caution, modularity can be taken too far. So, one point that I always like to make is you should ask yourself, how many files do I need to open to figure out where this function is defined or what it does? For example, if a design involves a whole string of nested function calls, where one function basically just calls another function from a different class, which in turn calls another function from a different class. Overuse of polymorphism can have a similar problem if you have too many layers of child classes. It also happens, I would say, when people use the auto keyword too much. It makes the code look cleaner when you write it. And I know people really like it in C++ because it's like, oh, it's more like Python. You don't have to worry about what the type is. It'll take care of it. But the thing is, it can actually make the code harder to follow for a reader because then they have to go figure out, well, what type is this? And if, as I've seen in several code bases, if they have to dive through 5 or 6 files in order to figure out what type that was, it's very easy to lose track. So my general rule of thumb when it comes to things like this is when the design pattern like this occurs within a single file, it's pretty manageable. It's not too hard to jump around a file. But across classes or namespaces, or literally across files, it's actually pretty easy to get confused. After diving through too many files, you might start to lose track of these. That's one thing to keep in mind. So the second principle for maintainability is simplicity. By the way, those pictures on the right are AI generated. I really just kept them because I thought, especially the one on the top right, was so bonkers that it was worth keeping. The prompt was an engineer frustrated with spaghetti code, and I look at it and I'm like, there's so many things wrong with that picture. He's facing the wrong way. His body's made of spaghetti. I don't know what happened to his arms, but I thought it was worth keeping in. Anyway, a common mistake that I've seen in my career is when people try to build flexibility into their designs prematurely, right? They usually do this with good intentions. They're probably trying to consider future extensions of their system, right? But the reality is it's actually easier to extend simple code than it is to adapt complex code. And any flexibility in the system, which is not necessary at the time that it's made, just adds complexity. For example, a common anti-pattern that I've seen many times is when people make an abstract class that just has a single child class. To make a trivial example, let's say I needed a banana object, right? And I'm like, oh, well, I can make a fruit class. And that way the banana can be a subclass of fruit, and we can do everything based on fruit, and it'll be more general, right? For one, like I was mentioning in the previous slide, it means that now people have to jump through more slides in order to get to the actual function that's actually being used whenever that object is being used. But also, a reader might happen upon this and assume that they're missing something. Because when they see the abstract class and then they see, well, there's only one child class, they might think, well, maybe there's another one hidden somewhere else, or there's some other utility here that I'm not finding. What's going on? They might get confused. The other thing is you might not anticipate the right challenges down the road, right? So say somebody does need to make a steak object in the future, right? Steak is food, but it's not fruit, right? And so now they need to either rework your existing fruit class and deal with any assumptions that you made about it being fruit, or they need to just make another abstraction. Neither of those are a great alternative. Whereas if instead you had just made a banana and that was the object that you needed, and you made that object, and then somebody comes along and they need steak, they can either identify, oh, okay, it would make sense for these things to share a food abstraction, or maybe it's not necessary. So that's what the bottom right picture is supposed to illustrate. Unused flexibility is like a giant empty mansion where all the rooms are empty and dark, except for the 1 or 2 that are actually used. All that space isn't helping anyone, and it could actually hurt if you get lost in it. An important point to make here, simple is not easy. Those two are not the same. My advice is think about it like when you're editing a paper. If you write a paper for an English class or for a publication, you write that essay or you write that paper, and then you do an editing pass and you edit it again and you edit it again. And usually when you're editing it, what you're doing is you're simplifying, you're condensing and clarifying. And I would think about this the same way. You think that simple is easy because when you look at it and read it, it's easy to understand, but that doesn't mean that it was necessarily easy to arrive at. An example I can give from my past, actually, for the beauty of simplicity, not specifically on code, but just in general. This is just a screenshot from a controller that I made early in my career, back when I had my own company. It was called the flocking controller, and it was for autonomous cooperative navigation of clusters of satellites. It was for a DARPA program called F6, right? So the goal here was to build, was basically saying, hey, what could we do if we, instead of having these giant monolithic satellites like the James Webb Space Telescope, for example, we could have a cluster of small satellites that would be less expensive to fire up individual replacements and less expensive to get them up in the air, et cetera. So at the time, several companies made designs which held the cluster of satellites to predefined trajectories. The problem with this is that these trajectories were linear, basically assuming Keplerian mechanics, if you're familiar with orbital mechanics. It basically assumes that the Earth is a perfect sphere. That's how the math is built. But actually, fun fact, the Earth is not a perfect sphere. It's actually kind of squashed. It's a little bit wider at the equator than it is in the other direction. And there's actually these two giant lobes. There's one where the Himalayas are, and there's one where the Rockies are that actually kind of bulge out a little bit. All of these effects make nonlinear forces on satellites in orbit. So the real point is that these nonlinear forces act on those satellites, and all the other designs wasted an enormous amount of fuel fighting those nonlinear forces because they treated them like disturbances of their linear trajectories. My flocking controller completely disregarded this concept of linearized trajectories, right? And instead, I just focused on a simple question. What does a group of satellites need to do in order to be a cluster? There's really just two things. They need to stay together, and they need to not hit each other. If they do that, then they're a cluster. So because of that, I was able to identify a very simple equation in the orbital mechanics frame. I mean, think of it as simple as like PV equals nRT. It was a very straightforward equation. And this equation could be used to calculate when two trajectories would intersect in the future. So basically, you, as a satellite, you could compute your trajectory. You could compute all the other trajectories of other satellites in your relative reference frame, and you could identify, there's going to be an intersection between our trajectories in 3 orbits or 5 orbits. And then doing that with that same equation, you could calculate a single burn that would essentially alter your trajectory and eliminate that collision or that intersection of the trajectories. Each satellite could compute this on its own. There didn't have to be any negotiation. They did need to talk to each other because they needed the state information of the other satellites, but they didn't need to negotiate about the burns. They would just do the burns when it was appropriate. And this controller was actually much simpler than the competing designs because it didn't fight the nonlinear forces. It actually ended up saving 95% of the fuel, ironically enough. So it was a significant fuel savings because it wasn't fighting those disturbances. Of course, like I mentioned at the beginning of this talk, I wrote a nice paper about this controller, but that was basically the end of it. It turns out that clusters of satellites are not actually practical. They end up costing a lot more fuel and weight than the big monolithic satellites. So in other words, we didn't understand the problem. All right, the last principle of maintainability that I'll cover is testability and debuggability. So the most important principle here is one way or another, you need to be able to test your system. If you can't test it, even if it works absolutely perfectly on the day that you write it, it will decay over time and eventually become buggy, unusable, or obsolete, right? First thing to think about, it's easier to design code for testability from the start than to re-engineer hard-to-test code. Code that's easy to test generally means the inputs are easy to construct and the outputs are easy to interpret. You've probably heard a term, test-driven design, before. The basic idea here is write the tests first and then build the code to pass the tests. It actually is really nice when you can do it. It's in particular what it's nice for is really forcing you to determine what the interface or the API is going to be for your system at the very beginning of the project. And that's a very nice thing to be able to do when you can. That being said, testing often does take a backseat during the prototyping phase of any project. It's not inherently bad, right? The goal of the prototyping phase, when you're in a commercial situation, is to answer this question of like viability as quickly as possible. Does this idea work? Is it worth pursuing? However, it leaves behind a code base that is often hard to test. Another saying that a friend of mine loves, which I think is a great saying, is there's nothing more permanent than a temporary solution. The reality is you probably won't have time to rewrite that system from scratch. So if you write your prototype with the thought of saying like, oh yeah, I'm not going to worry about anything about testability here. I'm just going to throw this away when I'm done. You're probably not going to have time. So even when you can't write the tests, designing with those principles in mind will make it easier to return and write the tests later. There's lots and lots of kinds of tests. Unit tests are very powerful. In particular, they're powerful because they can participate in the design loop. They're very fast and cheap to run. You can actually sit down and do develop, test, develop in a sit, right? And that is itself a powerful, accelerator. Of course, more complex systems, such as let's say you have a planning stack, right, for a vehicle, or even the optimization system that runs in that planning stack, they can be hard to isolate for unit tests. So that's where you need to have things like software integration tests. So that's just, for example, a vehicle simulation, right? They allow for testability of more complex systems. You can take the entire, software stack and run it in the simulation. Of course, the trade-off is that it's harder to test for specific conditions. I can't say, well, what happens when I take this particular branch of code? I mean, I can't do that easily. Sometimes you can figure out how to, stimulate the system in the right way, but it requires, more effort and sometimes isn't practical. So the counterpart to testability is debuggability. I'm not sure if that's actually a word, but basically how easy it is to track down issues when they occur. For simple systems, it's easy, right? You just add some print statements or you fire up GDB. But for more complex systems or for products, really what you're usually working with a log, right, where something bad happened. Your system was out there in the field, something happened, fired off a log, and you've got that log to work with, and that's basically it. So there's a couple really critical questions to consider. And the reason I really focus on these is because they are really accessible if you design for them from the start. And they're extremely hard to accomplish if you do not. So the two concepts, and they're very related, are determinism and reproducibility. Deterministic code means it runs the same way every time when you give it the same initial conditions. Doing things like iterating on unsorted lists or unsorted standard containers, that's not necessarily deterministic, right? If you're doing iterations and the order of the iterating matters, most compilers do not guarantee that order will stay the same with each run, and certainly not with each compilation. Reproducible code means that you can recreate the state of the system at any point where an issue occurred. So obviously code needs to be deterministic in order to be reproducible, generally speaking. But just being deterministic does not necessarily mean it's reproducible. What I'm trying to show in this picture here is like, imagine you've got a system. There's a lot of state in that system. And so the question you should ask yourself is, do you have access to all of that state? So that when something goes wrong, you can put it into exactly the state it was in when something went wrong. If you don't have the ability to do that, it may be very difficult for you to debug an issue. Yeah, so that's the thing to think about. Is there hidden state in your system that's not recorded in your log? All right, so we talked about maintainability. The other primary feature that I consider critical for mature code is robustness. Put simply, robustness means ability to continue operating when things go sideways. In some cases, elegant design can avoid or reduce edge cases. Right? This is rare, but it's powerful when possible. That flocking controller that I mentioned earlier is an example. We didn't have to figure out how to do disturbance rejection efficiently. if we didn't need to do disturbance rejection at all. So one important aspect of robustness is graceful fault handling. So this is literally first thing I'm going to talk about is in the execution path itself. You've got a program, it's running, and you need to be able to deal with something that's gone wrong. There's many ways to handle faults in code. There's lots of good ways to do it and lots of bad ways to do it. For the main execution path, it roughly breaks down into two categories: error transport and local healing. Error transport means you're sending the fault somewhere else. So think like C++ exceptions or error codes where the function is returning an error code instead of a result or in addition to a result. It's a great idea. It's a great component of a good fault management system. But keep in mind, the caller needs to handle a fault. When you're transporting a fault, the caller needs to handle the fault as well. So there's a concept usually used for this called contagion, which is what's the opportunity for a problem to spread. Local healing, on the other hand, means that you can rectify the fault in place, at least well enough that you can continue execute. So that's basically just saying like, hey, look, you've done something wrong here. I'm going to go register that error, but I'm then going to go figure out a way that I can at least continue operating this program safely. You might not end up getting a good result. So that it's much harder to guarantee that the result will be good if there's a fault like this, but at least you know that you're not going to crash out. Remember, when you're designing an API, one point I like to make to folks is you can't actually control the inputs to your functions. You can put limitations around those inputs, and it's encouraged to do so. But the thing is, you have to enforce those limitations in a graceful manner. I frequently see code where people have limitations and they say, this value has to be positive, and then they put an assert. The reason that's problematic is that it creates what I call landmines. What I mean by this is the code might work fine when you write it because everybody's using the API properly, but years later, when this code hasn't been modified or maybe even viewed for years because it's been working fine, somebody might write code that uses your library without reading the API carefully enough, and then they could suddenly generate graceless errors that they didn't write and they didn't expect. All right, so we covered fault handling within a process, and I think I even mentioned there, firing off a sort of a fault outside that process. There's a whole additional world of fault handling for a full integrated system. So like the zipline drone is a good example. Many different processes running on many different processors, right? So system-wide fault management involves handling system-wide faults with potentially system-wide responses. I also break this up into two categories: specific responses to specific faults and generalized responses to generalized faults. Generalized fault systems are really powerful for abstraction, right? So what they allow you to do is basically reduce the dimensionality of the problem, if you want to think about it in a general sense. It really allows for abstraction or separation between a problem and solution. As long as a fault meets a given set of requirements for a certain fault level, the generalized response behavior is adequate. For example, let's say, I don't know, we get a flat tire on the vehicle and we've got run flat tires. And so we know, hey, we can drive for 10 more minutes, but then we're going to have to stop. As long as that's able to meet the condition for, let's say there's a response, which is a pullover response, right? And the pullover response is, well, we guarantee that we can get the vehicle somewhere safe within 10 minutes. That fault would be able to raise that fault level, and that fault level would be able to trigger that response. And the response doesn't even need to know that it was a flat tire that caused that response. It's able to just execute its response. Specific fault responses, of course, can be much more targeted. A good example of a specific fault response is actually, you can't see it because this is the underside of the vehicle, but on the top, there's two motors and they're coaxial. The vehicle, the plane actually, the motors are powerful enough that the plane can fly on only one of the two motors. So if one of the motors breaks, it can fly on the other one. But one thing that we actually had frequently happen was one motor would break because the propeller would break. And when that happened, the motor would cause massive vibrations. And the problem was you couldn't tell which motor was causing the vibrations. So I wrote a very simple response circuit, which was when these vibrations are detected, it turns one motor off, and then it essentially evaluates in the next second to see if the vibrations have stopped or if they've continued. If they've stopped, then you know that this the motor you turned off is the one that is bad. And if they continue, then it's the other one that's bad. You turn that one off and turn your first one back on. The thing to remember about specific responses is that having a lot of them can create a really complex system because your whole system is going to have to handle the every possible combination of individualized responses that are occurring. So that's the thing to keep in mind about that. Use them sparingly. Okay, last aspect I want to discuss is predictability. Okay, predictability improves robustness by reducing the unique situations that have to be handled. To use another example from Zipline, the vehicle used the CAN bus for communication between processors. This is common architecture and safety critical applications. And one of the things about CAN is there's a limited bandwidth. We designed an error signaling system where processes could send fault messages onto the CAN bus when something went wrong. And we discovered pretty quickly that in some cases, these error signals would cascade and cause other error signals because error conditions in one component would cause error conditions or responses in other components. And then at a certain point, the error messages themselves were so prolific that they actually overwhelmed the canvas and created a whole new error condition. So it might seem counterintuitive, but the solution to this problem was actually to have all the processes send the error signal all the time, like a heartbeat. And they would just say everything's okay when they weren't, when there was no problem. Now, of course, this did force us to reduce and streamline the communication happening across the bus, but it meant it led to more reliable performance. It meant that when something went wrong, we knew that we were not ending a new condition, a new different situation that the system had to handle. Basically, the moment when something has already gone wrong is the very worst time to put the system into a new state or a less tested state. So basically, for a product, consistency is more valuable than optimality in most situations. All right, if I could sum up the point of this lecture as simply as possible, it would be this. Ideas are cheap. Execution is the tough part. A funny thing about startups is that people often think that their ideas are the valuable thing. They covet their ideas. They keep them secret. They operate in stealth mode. Lots of people often have similar ideas. The ones that are successful are the ones that can run the marathon to cross that gap between a great idea and a world-changing product. Any questions?
Let's thank Jeffrey. We got time for some questions.
So regarding readability of the code, so what's your idea with regards to the all these toolings that we have right now that allows us to produce more readable code? And what I mean by that, from my personal experience, I've seen these rules that we have to follow for generating maintainable code, readable code are ever changing.
Mm-hmm.
For example, even prior to this whole AI stuff, before LSPs and formatters became mainstream, we had all these formatting rules that. Mm-hmm. So and the whole idea behind that was to format the code in a way that each change would result in the least amount of formatting changes, right? But after formatters and after LSPs, now we don't have a lot of them at least. Or the auto keyboard that you've mentioned. Right now, we have LSPs that can produce emulations, let's say, and so your IDE can kind of hint you.
Yeah.
So what's your point of view on this?
Yeah, I mean, obviously, the ability to use LLMs in the loop, during design, I think is certainly going to, be a revolution. Just like every technology, can be a little bit of a revolution. I do think that the question of readability is something that changes over time. It is, largely a question of style, and style changes over time. If we have systems and they can tell us exactly what we need to know, then good, then that's great. Then we can use those systems and that's good enough. For me personally, the advice that I give when it comes to using LLMs in that manner is, at the end of the day, you are still the person who's responsible for the code that you add to the code base. At least right now, my feeling on LLMs is that they're a very powerful tool in the right hands, but they're very dangerous when not used carefully, because they can make bad code. And if the person using it does not understand that code is bad code, then you can end up very quickly with a system that's impractical. Similarly, if they give you a wrong answer and you come up with a wrong understanding of the system, and that wrong understanding is, for one reason or another, not corrected, it can lead to problems downstream. The other thing that I'll say about using those kinds of systems is one reason I'm a little reluctant to advise it is that when you're writing code, you're also learning. You're learning about the code that you're writing. You're learning about the code around the code that you're writing. You're learning about the overall system and how it interacts with that code. When you sort of abdicate that responsibility more and more to an LLM system, it may be very soon that the quality of the code is just as good or maybe even better than it would be if you'd written it, but you are robbing yourself of that opportunity to learn. And that may, in the long run, not be good for you from an experience standpoint. So my advice is those things are really powerful when used in the right hands, but also can be really dangerous.
Other questions? Anyone else? Yeah, go for it.
And so about like reproducibility and like debuggability, as you said. So what was your experience with like multi-threaded or like multi-processor kind of code, and like how do you debug those usually? And like have you ever tried to like consider functional programming or like functional paradigm mindset into your to like bring them into your code?
Yeah, that's a great question. And yes, actually, the answer is absolutely. Actually, our planner is designed with a functional paradigm. And the reason is exactly to address that issue that I brought up about hidden state. We have a bunch of subcomponents in our planner, but the subcomponents are actually defined as namespaces. They're not even defined as classes, so that we can't have class variables that don't end. Like we have basically one top level data structure, and that top level data structure stores all of the data of the state in the system, and all of the subcomponents are basically designed functionally where they take in that state as the input to the function and they output that state as an output from the function. To your question about multi-threaded, yeah, multi-threaded means multi-dangerous. I think the answer is still the same, which is that if your system is fully deterministic and it's reproducible, you would be able to track down where the problem is happening and in which thread. But if it's not, then you really open yourself up to a world of really, really challenging debugging sessions. And that question of determinism itself will force you to deal with things like, race conditions and any kind of conflict between the threads. Because if you have anything like that, your code won't be deterministic, or at least it won't be reproducible.
Anyone else? No? All right, let's thank Jeremy again. You do want to talk more, he'll be in GMCS 418 around 1:30 for at least an hour. So yeah, some time slots for you to drop by and just chat. Thanks for coming. I can find you. All right.